that it contains fractures of one type or another which render its structure discontinuous? Yes. Then a clear distinction must be made between the rock element or this rock material on one hand and the rock mass on the other hand. So the rock material is the intact rock we are describing, okay? And the rock mass is the entire surface of the rock we are looking at, which contains all the other properties that we have seen. That is the rock mass. So what are some of the, so rock masses are discontinuous and often have what? They are usually heterogeneous and anisotropic. They have these two properties most of the time. And so the nature and distribution of these structural features within the rock mass are known as a rock structure. So let's have a look at the properties of the 2 or 3, I think they are 4, yes, 4 major rock mass classifications that have been used, or usually geotech officers within our various mining companies, they either use the mining rock mass classification, the KO system, the RMR, and then RQD. So these are systems they have been using, and sometimes the rock mass structure. So we want to have a look, an overview of these properties, and then we move on. And the principles under which they operate. So the rock mass structure rating, we have the rock mass rating, and then we have the rock tunneling quality index, which is also known as the KO system, and then the rock geological strength index, which is the GSI. So Benioski proposed the rock mass rating. So his rock mass rating, he has 6 properties that he uses in determining his rock mass rating. The first property is a mechanical property. So you go back to the lab, the test that was conducted, you pick the test value, he needs it for his test. Then there's another method that was proposed by somebody to determine the rock mass quality. So let me see if I can see that and discuss that here before we come back to it. So the rock quality index, which is called the RQD, what does that mean? It means if I drill a rock sample, a core, I want to find out or measure what percentage of the entire core length. So let's take the entire length is 100 meters. I want to find out of the 100-meter length, what is the quality index? As in, what is the portion of the rock that is of good quality, that is not broken? So I drill a core sample out of a rock mass, and I want to check along the length that I have taken out. I want to measure what portions of it is not broken to a certain length that is not ideal. And so measuring that is what we term as the RQD. So let's see this. So the RQD is based on the modified core recovery. So how does the person determine this RQD? Let's look at this image. So when we drill, we place these core samples inside the core logging boxes like this. And as we see them this way, we try to measure at what point. So let's take, for example, this particular rock sample is purely broken. So we can't use this to determine that the rock is of high quality or not. And so the DeRay et al. That proposed this principle are saying that if I want to determine a rock mass, its quality, the length of a core, the quality of the length of a core, I should use this formula. And how do I determine that? He says that I should check the entire length of the core sample that was drilled and see any sample that is greater than 10 centimeters should be considered. If it is less than 10 centimeters, I should ignore. Okay, so length of core pieces greater than 10 centimeters. So let's take the entire core length that we have here. From this point to that point, I'm labeling it A. At point A, that sample, although the core sample is broken, but I could get a section that's about 38 centimeters. And with that 38 centimeters, it is considered in the calculation of the quality of the core. This is 17. 17 is greater than 10 centimeters, so it will be considered. If I pick these other sections, they are all broken or shattered into some pieces. And so in that case, they are less than, none of those pieces there is up to 10 centimeters. And so I can't use it. This is up to 20 centimeters, so I can. This is up to 20 because it's just a crack along it, but not shattered into pieces. So that is why it is measured. Then I have another 35. So to determine the strength of this rock, the quality index of this rock, I will sum all those portions of the rock that were ticked as good and then divide it by the entire length of the core. And the entire length of the core was 200 centimeters. So I have 38 plus 17 plus 20 plus 35. And that will give me the entire length of the rock. So let's check that and see. There was an omission in this calculation. That's why I'm not using that one. The 35 didn't come, but the answer is correct. Good. Yeah. So this RQD value we have obtained is what is needed as part of the things this Benieski man. So he was also a smart dude, you know. He decided to read to check those properties that other people have proposed, the rock mass classification that people have proposed and they think is good. And then the mechanical properties that we think influence the rock the most. So his principle will talk about the uniaxial compressive strength, which means he has covered mechanical property of the rock. Then he came to the quality of the core, which is this. Then now he goes to the geotechnical mapping to check the discontinuities visually, give descriptions and rate them. Then he adds that to his principle. Then what are the conditions that these discontinuities are subjected to as of the time we were doing our mining activity? He will quantify that and assign rating and then capture that into his principle. Then again, do we have any water issues there? If we have issues of water disturbing our operations, he will quantify that again and fit into his model. Then finally, he looked at the orientation of the discontinuities. Are they in favor of our excavation activities or they are not in favor of our excavation activity? That again, this man will look at it and quantify that in terms of rating and factor that into his model. So out of the box, you just see that, oh, this is an ideal. So assuming you were to go out there as a geotechnical officer and these packages were for sale, the RQD alone was a package which you should use to design. And then Tezagi's approach was also in a box, also on the shelf for sale. I think you will go for the RMR. Is that not it? Because it is capturing almost everything, if not all, most of the things that we encounter on the field. So now, let's move on to how his method is being used. So he says that in applying this classification system, the rock mass is divided into a number of structural regions, which is what we just looked at. And each region is classified separately. So the boundaries of the structural regions coincide with a major structural feature. such as a fault or with a change in rock type. So if you have a particular rock type, you have to do this thing to it, this particular RMR system, do it to that rock type. So for example, in your mine, if you have certain section of your mine having only conglomerate, go and deal with it. Use the rock mass rating system to have an idea how your conglomerate behaves. Get a rate for it. Go and do the same for your phyllite and do the same with your granite. All of these things, then each time you are to mine in a granite zone, you have an idea what the strength properties or the classification properties are. That is exactly what this man's principle works. Then the rock mass rating is presented in a table. So let's see. The ratings are summed to give a value. So let's see this. So on this table, the first thing we are looking out for, number one, he says that we should check the strength, the mechanical property of the rock. What value did we get? So if we check the mechanical property of the rock, for example, the examples we did yesterday, or is it the last time we checked, what were some of the things we got? When we tried to calculate for the UCS value, what value did we get? 82, right? If you can remember. Yes, when we calculated for this and decided to do the correction for it, we got a value of 82 and we compared it on this table by multiplying 23 by 3.6 or so. 23 times 3.6 and we got 82.8. So that 82.8 megapascal value we got, we are assuming that to be the rock property we are using on this table. So assuming we did our test and our rock property was 80. So if you come to the one where I have circled, you have the various rock properties and the ratings. So check along this line below that, on top of the tick line. So he says that if you have a point load strength index, remember I said if you have a point load strength index value, you can use it to estimate a uniaxial compressive strength value. But in this case, we are lucky we got a point load strength value of 3.6. So our 3.6 is somewhere here. So what will be the rate for 3.6? That will be 7. Thank you. So that is 7. And remember when we converted to the uniaxial compressive strength, we got 82.8. And 82.8 is also falling between 50 to 800. Is that not it? And so it's still 7. Then, having gotten that, let's assume that same rock sample, the core sample was what we used. The core sample, which is the RQD value of 55, was what we got. So we are going to use the 55, and 55 will fall somewhere here. Is that not it? So with 55 falling somewhere here, the rating is going to be 13. Then now, we go out there and check the spacing and other things that the spacing discontinuities or spacing of discontinuities. So the spacing of discontinuities, you have to check the rating. If you measure any spacing, assuming I have a crack between the rock and you check from the crack the distance between the two surfaces that are forming the crack, if you use your tape to measure and you are getting a very wide value, which is greater than 2, he says that you should rate, okay, which is greater than 2, a spacing of discontinuity. That is, this one is specifically talking about if I have one discontinuity here, and then I have to walk about 2 meters or 3 meters before I see another discontinuity. That is the spacing we are referring to in this sense. So for example, the discontinuity I showed you earlier, you realize that if you see one crack or one line along the rock, then you have to walk a certain distance of about 2 meters before you see another. Then it means the rock is good. And so you can rate it as 20. So you see a crack, then you walk another distance before you see another crack, then you rate it. So in this case, what value should we assume to be our discontinuities? Okay, with a 10. All right, so we are picking a spacing of about 200 to 600 millimeters. So when we see one spacing or discontinuity, we walk 600 millimeters before we see another. Then we are going with 10 as the rating. Then the next one is condition of the discontinuities. What are the conditions of the discontinuities? And it says we should look for table E. So table E, here they are. So to check continuities there, we will look for one, discontinuity length. What are the lengths of the discontinuities? If the length of the discontinuities are greater than or less than 1 meter or greater than 20 meters, then it's not good how they persist. So if you have separation and aperture, you have to rate that. If you have infilling, it means that you have a crack and then it has been filled with some soft material. You have to rate it. And then the weathering condition, you look at the surface and it's all weathered. You saw the sample I showed you, it was brownish in nature. So with that behavior, you have to rate them. So let's see, what rating can we give to this one? So if we come here, discontinuity length, what value should we assume? 3 to 10. So the young man wants a rate of 2. Yeah. Separation aperture. So separation aperture is referring to the gap. So, excuse me, let me pick the sample. So if I have this sample, the gap that is this between this, so this is the crack, you are able to see it. What is the gap? That's the aperture, the space. That's the separation aperture. Then when we go to the top, discontinuity length. That's why they stated the word the persistency. So I have seen one here. How far will I travel before I see another? So if they keep persistent, so for example, I see this, I see another one this way, I see another one. So I am measuring the distance from here to there, from here to there, keep measuring to see how close these discontinuities are to each other. Then I'm referring to discontinuity length. So now we are looking at the separation aperture. So we are picking 5. Then the roughness. When you look at the surface of the discontinuity, is it rough or smooth? If it is very rough, we pick 6. Then we have infilling. If there are any samples or clayey materials sitting within the aperture, the space that is there, what should we go for? 2. Then the final one, is it weathered or unweathered? The surface of the
discontinuity. I'm saying 2 there 2 times.
Is what?
I'm seeing hard filling greater than.
So just tell me the rating. So we have soft filling less than 2, and then hard filling if it is greater than 5. So the 2s are 2. So which one are you picking?
Less than 5.
Less than 5. So then let's go for weathering. How will you describe the weathering process? Is it weathered or unweathered? The surface of the discontinuity in terms of weathering, which is a measure of durability. So you want to check that. Let's give any value and move on. Slightly weathered. So now you are going to sum these numbers. So we have 5 plus 5, 10 plus 5, 15 plus this 17. So we will go back to the first table we were playing with, and with that one, we got 17 as our value. So you see, so it means that our original value, instead of just looking at these two, have just stated something. We went there because we wanted to dive deeper into these properties that are there. And so you see, none of our values is the value we got is not here. It means that we have gotten deeper into the description rather than looking at it at the surface. And so we have 17 for this. Then let's see, ground infilling. Ground infilling. So what do you have? So here we are looking at groundwater. So you want to see how water has affected the excavation or the activity you are doing there. And so we have groundwater infill per 10-meter channel length. So at every 10-meter per length of the tunnel or whatever activity you are doing, do you see water filling up the space or the place? And then joint water pressure, the amount of pressure that is being exerted onto the surface. So you use these conditions to describe. So in other words, you can just say the general conditions of the place. Is it completely dry? Is it damp? That is, it looks like quite wet, moist in some form. Is it wet or it is dripping? You see water coming out of the walls, just like it rains and you see your roof dripping water gradually. And or the water is just flowing like a river. So if you use these general conditions, then you can rate the rock mass. So what are we going for? Completely dry, damp, wet, dripping, or flowing? What is our condition? Dripping. You use 17 something, 17 level. All right, so now that we have gotten this, to determine the RMR value, which is not the final one, we have to sum these, the blues. 1, 2, 3. So 7 plus 13, 20, plus 10, 30, plus 17, 47, plus 7. What will it be? 54, right? Wow. So then, the next thing we do is to check whether there are any unfavorable conditions that may affect in terms of strike and dip orientation. Then we subtract them from this value we have gotten. Because if you add this, let's say you add this 15 plus 20 plus 20. So 20 plus 20, 40 plus this 55 plus this 85 plus this 100. So the entire rate is 100. The highest is 100. And we got 54. So now we have to go and check the strike and the dip orientation of the stope. How are they? If it is for slopes, okay, the orientation, if it is for slopes, is it favorable? It is very favorable, then 0. If it is favorable, you subtract a certain value. If it is fair, these are the ratings you subtract. If it is unfavorable, you subtract some ratings based on the activity you are doing there. So if we are dealing with tunnels and mines, we are dealing with tunnels and mines. So this is where we fall. So with tunnels and mines, let's ask ourselves, our 17 level, the stope we are dealing with, how is the strike and dip orientation? Are they very favorable to our excavation, or they are favorable, or fair, or unfavorable, or very unfavorable? They are favorable, so -2. So we subtract 2 from our 54. So now we will add all of the stuff there. Okay, so it says that the effect of discontinuity, strike and whatnot. So then we have strike parallel or perpendicular to the channel axis, or strike parallel to the channel axis. So again, we have to check this. So in order for you to be able to describe the first instance here very well, you can come back to this table and use this. If you want to have a fair idea of your description, you can come here. When do we say it is favorable? When do we say it's unfavorable? So you said favorable. Favorable means our drive is with a dip of 20 to 45 degrees and is perpendicular. That is why you chose favorable. So now, if you subtract the 2 from the 54, what do we have? That would be 52%. So finally, the rating of our rock is 52. So it says classification parameters plus the discontinuity orientation adjustment. And so you have your RMR of 52%. And then we are done.